Welcome to our exploration of the first law of thermodynamics. In this video, we'll unravel the fascinating world of thermodynamics, a branch of physics that deals with energy, heat, and work. We'll begin by understanding the historical context and how thermodynamics evolved as a distinct field, eventually merging with mechanics through groundbreaking experiments. By the end of this journey, you'll have a solid grasp of internal energy, heat, work, and the powerful law that connects them all. So let's dive in and discover how energy moves and transforms in the universe around us. Thermodynamics and mechanics were once considered separate branches of physics. This changed around 1850, thanks to experiments by James Joule and others. They discovered a connection between the transfer of energy by heat in thermal processes and the transfer of energy by work in mechanical processes. This led to a broader understanding of energy, including the concept of internal energy. The principle of conservation of energy emerged as a universal law of nature, forever changing how scientists viewed the physical world. In this chapter, we'll discuss internal energy, the first law of thermodynamics, and how this law applies to various systems. The first law describes situations where the only energy change is internal energy, and energy transfers occur through heat and work. We'll also look at work done on deformable systems, such as gases in cylinders. By the end, you'll see how these concepts fit together to explain everyday phenomena and complex scientific processes. Internal energy refers to all the energy contained within a system that is associated with its microscopic components, its atoms and molecules. When we talk about internal energy, we're considering the system from a reference frame at rest with respect to its center of mass. This energy includes the random motion, rotation, and vibration of molecules, as well as the potential energy between them. It's a key concept for understanding how energy is stored and transferred within matter. It's important to distinguish internal energy from other forms of energy. For example, the kinetic energy due to a system's motion through space is not included in internal energy. Instead, internal energy covers the kinetic energies from random translational, rotational, and vibrational motion of molecules, plus the potential energy between them. This distinction helps clarify what changes when energy is transferred as heat or work. Heat is defined as the transfer of energy across the boundary of a system due to a temperature difference between the system and its surroundings. It's crucial to use the term correctly. Heat refers only to energy in transit, not energy contained within a system. Many common phrases misuse the word heat. Remember, you can't talk about the heat of a system. Heat only exists during energy transfer caused by temperature differences. Historically, the calorie was used as the unit for heat. 1 calorie is the energy needed to raise the temperature of 1 gram of water by 1 degree C. In food, the calorie is actually a kilocalorie. The U.S. customary system uses the BTU, or British thermal unit, which is the energy required to raise 1 pound of water by 1 degrees F. Today, the standard unit is the joule. Understanding these units helps us compare and calculate energy transfers in different contexts. James Prescott Joule, a British physicist born in 1818, played a pivotal role in establishing the principle of conservation of energy. Largely self-educated, Joule's research demonstrated the equivalence between mechanical energy and internal energy. He determined the amount of work needed to produce 1 unit of energy, laying the foundation for modern thermodynamics. His experiments changed our understanding of how energy can be transformed from one form to another. Joule's experiments established the mechanical equivalent of heat. He showed that mechanical energy could be converted into internal energy. In his famous setup, falling weights turned paddles in water, causing its temperature to rise. The decrease in potential energy of the weights equaled the work done on the water. This experiment demonstrated that energy could be transferred and transformed, but never destroyed. Joule found that about 4.18 joules of mechanical energy were needed to raise the temperature of water by 1 degree C. Later, more precise measurements determined that 1 calorie equals 4.186 joules. This value is now known as the mechanical equivalent of heat. It highlights the direct relationship between mechanical work and heat, reinforcing the idea that energy can change forms but is always conserved. Heat capacity, denoted as C, is the amount of energy needed to raise the temperature of a particular sample by 1 degree C. If energy Q produces a temperature change T, then the heat capacity tells us how much energy is required for that change. This property varies between substances and is crucial for understanding how different materials respond to heating. Specific heat is the heat capacity per unit mass of a substance. It measures how thermally insensitive a substance is to added energy. The higher the specific heat, the more energy is needed to change the temperature of a given mass. The equation Q equals mc delta is commonly used, where Q is energy, m is mass, C is specific heat, and delta is the temperature change. Different substances have different specific heat values. For example, water has a specific heat of 4186 J/kg degrees C, much higher than metals like copper or gold. This means water requires more energy to change its temperature, which is why it plays a significant role in climate and weather. Knowing specific heat values helps us predict how materials will respond to heating or cooling. Change in internal energy of a system can be identified using the equation delta int equals Q, assuming no thermal expansion or contraction. Internal energy can be changed by transferring energy into the system by any mechanism. This also shows that temperature is related to the energy of the molecules in a system. Understanding this relationship is key to mastering thermodynamics. Specific heat technically varies with temperature, but for small temperature intervals, this variation is negligible. For example, water's specific heat changes by only about 1% between 0 degrees C and 100 degrees C. Unless stated otherwise, we treat specific heat as a constant in calculations. This simplification makes it easier to analyze energy transfers in practical situations. Water has the highest specific heat among common materials. This property is responsible for many weather phenomena, such as moderate climates near large bodies of water, global wind systems, and land-sea breezes. Because water can absorb or release large amounts of energy with little temperature change, it acts as a thermal buffer in the environment. Calorimetry is a technique for measuring specific heat. It involves heating a material, adding it to water, and recording the final temperature. The calorimeter is an isolated system, so conservation of energy applies. The energy lost by the hot sample equals the energy gained by the water. This method allows us to determine unknown specific heats using simple experiments. In calorimetry, sign conventions are important. If the temperature increases, both Q and delta are positive, indicating energy enters the system. If the temperature decreases, Q and delta are negative, meaning energy leaves the system. The negative sign in the calorimetry equation ensures consistency with these conventions, making calculations reliable. The calorimetry equation relates the masses, specific heats, and temperature changes of the water and the sample. It's written as TFTW equals mx TFTX. This equation can be solved for the unknown specific heat. In practice, the mass of the container is often neglected if it's much smaller than the mass of water. Let's look at a practical example. Suppose an ingot of metal is heated and dropped into a beaker of water. By measuring the equilibrium temperature, we can calculate the specific heat of the metal using the calorimetry equation. This hands-on approach demonstrates how energy conservation allows us to determine material properties in the lab. A phase change occurs when a substance transitions from one form to another, such as solid to liquid melting or liquid to gas boiling. During a phase change, the temperature of the substance remains constant, even though energy is being added or removed. The energy goes into changing the molecular arrangement, not raising the temperature. Latent heat is the amount of energy required to change the phase of a substance without changing its temperature. The value of latent heat depends on the substance and the type of phase change. For example, melting ice or boiling water both require energy input, but the temperature stays the same until the phase change is complete. Different substances have different latent heats for fusion melting and vaporization boiling. For instance, water's latent heat of fusion is 333,000 J/kg, and its latent heat of vaporization is 2,260,000 J/kg. These values are crucial in understanding natural processes like melting ice or boiling water, and they play a role in weather and climate. Let's visualize the process of heating ice to steam. The graph shows energy added versus temperature. Starting with ice at -30 degrees C, energy is added to warm the ice, melt it, heat the water, boil it, and finally heat the steam. Each phase change appears as a flat region on the graph, where temperature remains constant while energy is absorbed. In the first part of the graph, we start with 1 gram of ice at degrees C. As energy is added, the temperature of the ice rises to 0 degrees C. This requires 62.7 joules of energy. This stage involves only warming the solid phase, with no phase change yet. Once the ice reaches 0 degrees C, it begins to melt. During this phase change, the temperature remains constant, even as energy continues to be added. Melting 1 gram of ice requires 333 joules. This energy goes into breaking the bonds between water molecules, not raising the temperature. After all the ice has melted, the water is heated from 0 degrees C to 100 degrees C. This stage requires 419 joules of energy. The temperature rises steadily as energy is added, with no phase change occurring during this interval. At 100 degrees C, water begins to boil. This phase change requires a large amount of energy, 2,260 joules for 1 gram, without any increase in temperature. The energy is used to break intermolecular bonds and convert liquid water into steam. Once all the water has turned to steam, any additional energy increases the temperature of the steam. In this final stage, 40.2 joules are needed to raise the temperature from 100 degrees C to 120 degrees C. The total energy added from ice at minus 30 degrees C to steam at 120 degrees C is 3110 joules. Supercooling occurs when liquid water is cooled below 0 degrees C without freezing. This happens if the water is perfectly still in a clean container. The water needs a disturbance to start forming ice crystals. Once disturbed, it freezes instantly, and the released energy brings the temperature back to 0 degrees C. This unique property is due to the molecular structure of water. Superheating happens when water is heated above 100 degrees C without boiling. This requires the absence of nucleation sites, such as scratches or impurities. When disturbed, the superheated water can boil explosively, rapidly forming bubbles and ejecting hot water. This phenomenon is important to understand for safety in both laboratory and kitchen settings. State variables describe the condition of a system. These include pressure, temperature, volume, and internal energy. For an isolated system, all parts must be in thermal equilibrium, meaning uniform pressure and temperature throughout. State variables help us define and analyze the system's properties at any moment. Transfer variables, such as heat and work, are only non-zero when energy is transferred across a system's boundary. They are not associated with a specific state, but with changes between states. Depending on the direction of energy flow, transfer variables can be positive or negative. Work can be done on deformable systems, like gases in a cylinder with a movable piston. When a force is applied to compress or expand the gas, energy is transferred as work. The process is considered quasi-static if it happens slowly enough for the system to remain in equilibrium. The work done is related to the change in volume and pressure. The work done on a gas is given by dW. If the gas is compressed, dV is negative and work is positive. If the gas expands, dV is positive and work is negative. If the volume stays constant, no work is done. The total work is the negative area under the PV curve between initial and final states. PV diagrams plot the pressure and volume of a gas during a process. The curve, or path, shows how the system changes. The work done on the gas equals the negative of the area under the curve. This visual tool helps us understand and calculate energy transfers in thermodynamic processes. The work done on a gas depends on the path taken between initial and final states. For example, compressing a gas at constant pressure yields different work than compressing at constant volume or along an arbitrary path. PV diagrams help visualize these differences, emphasizing that work is path-dependent. In one example, the volume of a gas is reduced at constant pressure, then the pressure is increased at constant volume. The work done is calculated as W equals P(I) V F VI. This demonstrates how the sequence of steps affects the total work done on the system. In another example, the pressure is increased at constant volume, followed by a constant pressure compression. The work done is W equals PF VF VI. Again, the path taken determines the amount of work, highlighting the importance of process details in thermodynamics. When both pressure and volume change continuously, the work done is an intermediate value between the previous examples. To calculate the exact work, the function P, V, must be known. This reinforces that work depends on the specific path taken during the process. Energy transfer into or out of a system depends on the process. An energy reservoir is a source so large that its temperature doesn't change during energy transfer. For example, a gas in contact with a reservoir can absorb heat while expanding, with the reservoir maintaining constant temperature. In an isolated system, no energy is transferred by heat or work. For example, if a gas expands into a vacuum inside an insulated container, it does no work and no heat is exchanged. The internal energy remains constant, and no temperature change occurs. This scenario illustrates the importance of system boundaries in thermodynamics. The first law of thermodynamics is a special case of the law of conservation of energy. It states that the change in internal energy of a system equals the energy added as heat plus the work done on the system. This law underpins all of thermodynamics and ensures that energy is always accounted for, no matter how it is transferred or transformed. The first law applies to various processes: adiabatic no heat exchange, isobaric constant pressure, isovolumetric constant volume, and isothermal constant temperature. Each process has unique characteristics and equations. For example, in adiabatic processes, all energy change is due to work, while in isothermal processes, any heat added is balanced by work done by the system. Energy can be transferred by conduction, convection, or radiation. Conduction involves direct transfer of kinetic energy between particles, convection involves movement of matter, and radiation involves electromagnetic waves. Each mechanism plays a role in how energy moves through and between systems, affecting everything from weather to technology. Thermal conduction is the process of energy transfer by heat through direct contact. Metals are good conductors because their electrons move freely, while materials like asbestos and gases are poor conductors. The rate of conduction depends on the material's thermal conductivity, the area, and the temperature gradient. Different materials have different thermal conductivities. For example, silver has a high value, making it an excellent conductor, while air and wood have low values, making them good insulators. These properties are essential for designing buildings, electronics, and everyday objects. Convection transfers energy by the movement of fluids, either naturally or by force. For example, warm air rising above a radiator creates a current. Radiation transfers energy via electromagnetic waves, requiring no physical contact. All objects emit radiation, and the rate depends on temperature and surface properties. Stefan's law describes the rate of energy radiation, P equals sigma AET4. Here, sigma is a constant, A is surface area, E is emissivity, and T is temperature in kelvins. An ideal absorber or black body has E equals 1 and absorbs all incident energy. Black bodies are also perfect radiators, making them important in physics and engineering. Dewar flask, or thermos bottle, is designed to minimize energy loss by conduction, convection, and radiation. It uses a vacuum between walls to prevent conduction and convection, and a silvered surface to reflect radiation. This clever design keeps liquids hot or cold for extended periods, demonstrating practical applications of thermodynamics.